Number 5. A ray of light strikes a thick sheet of glass at an angle of 25 degrees. Find the angle of the ray reflected with respect to normal. So a lot of these problems have to do with really making sure that you read it correctly. It's asking for the reflected angle. So the law of reflection tells us that when you have an incident angle, the reflected angle, so this is the incident right here, this is the reflected angle, they're going to be the same. Number 6, so radio waves have a wavelength of 100 meters. What's the frequency? So we're given the wavelength right here. We want to know the frequency. Radio waves are electromagnetic waves, so they travel at the speed of light. So we can use the relationship between the speed of light, the wavelength of a wave, and the frequency of a wave, and just solve for the frequency, which is c over wavelength. Make sure that for c, you're plugging in 3 times 10 to the 8. And you should get answer B. Number 7, we're given the index of refraction of the plastic and the velocity of the beam of light before it enters the plastic is this. What's the velocity inside the block? So you notice that the velocity before it enters the plastic is the same as the speed of light in a vacuum, which is what we would expect because it's incident from the air. So that's why it has this speed in air. So the index of refraction relates the speed of light in vacuum, which is c, to the speed of light in the medium that we're going to. So we're solving for v. The speed of light in our medium is going to be c divided by n. And both are given. Number 8, a light ray is incident on an air to glass boundary and is refracted. Find the index of refraction. So this is a Snell's law problem. Again, we try to picture it. Sorry, my lines aren't very straight. So we have an angle of incidence right here. Call it angle 1, theta 1, and that's the 30 degrees right here. And then we're going to extend our normal and draw the angle of refraction, which is right here, angle 2, and that's the 21 that we're given right here. So when we define our angles, we also want to define the index of refraction, n1 here is equal to 1 because we're in air, and we're looking for n2 of the glass. So we use Snell's law, n1 sine theta 1 equals n2 sine theta 2, and we solve for n2. We will get n1 sine of theta 1 divided by sine of theta 2. Sorry about that. Here we go. Plug in the numbers and you'll get 1.4. Number 9, we're given the wavelength of our monochromatic source. Monochromatic just means it has one frequency, and it's 490 nanometers. What's the wavelength when it passes through a liquid where the speed is 2.4 times 10 to the 8? So I'll write the givens here since we don't have room up there. So the wavelength in vacuum is the one that we are given, 490 nanometers. And the speed is v, that's the 2.4 times 10 to the 8. So what's happening here is that our light source was slowed down, right? It's not going as fast as the speed of light. That means it was going through this liquid which had some kind of index of refraction not equal to 1. So we know that the index of refraction is c over v. We could solve for it if we wanted to, but we also know that this index of refraction tells us about how the wavelength of light changes as it goes through that medium, through the dispersion relation here. So we can just set c over v equal to lambda naught over lambda. Lambda is the wavelength of the light in the material, in that liquid that it's going through. So that's what we're trying to solve for, is lambda. So that's going to be equal to lambda naught times v over c. Remember again that c is equal to 3 times 10 to the 8 meters per second. Number 10. We have flint glass that's holding some benzene. What's the critical angle for internal reflection when it is incident on the glass to liquid? So first of all, for internal reflection to occur, the ray must be going from a high index to a low index, and that's what it's doing. It's going from a 1.66 index, so I'll call this N1, to N2, which is a lower index. So the critical angle is given by sine of critical angle equals N2 over N1. Always make sure that N1 is greater than N2. If you end up putting it backwards by mistake, you won't be able to take the inverse sign anyway, but it's just very important that it goes from high to low, otherwise total internal reflection is not possible. So you solve for the critical angle by taking the inverse sine of N2 over N1. Make sure your calculator is in degree mode, and you should get 64.7.